Slide 1. This first slide is all about how to create a My block. Basically, this process is like building your own reusable command for the robot. You get to name the block, decide what inputs it needs, and then save it as your own mini tool. It's like teaching the robot a new word so you don't have to repeat the same code. First, you choose a name for your block. Then you set input bubbles and text labels, just like the ready-made blocks that come with your Spike kit. Finally, you place those red bubbles in the right spots to complete the definition. Let's go to the next slide. Slide 2. On this slide, we're seeing how the degrees for My block works. Essentially, this block tells the robot how many degrees it should turn when making a move. For example, a full circle is 360 degrees, a half circle is 180 degrees, and a right angle corner is a 90-degree turn. What we see here is that the block sets the robot's movement speed lower, like at 20%, to make those turns accurate and sharp. After the turn, it returns to the normal 30% speed for following the line. This way, the robot moves smoothly and doesn't overshoot. Let's head on over to the next slide. Slide 3. This slide deals with a calculation you need to do inside the line follower My blocks when you're using distance. We've got a relative position block that tracks how many degrees your motor has rotated. When your robot moves forward, that number goes up, and when it reverses, it decreases. If the motor does a full 360-degree rotation, that's one full turn of the wheel. To convert those rotations into real-world movement, we divide the position by 360 and multiply by 17.5, which is the centimeter distance of one full rotation for these standard Lego wheels. That's how we turn motor spins into real-world movement. Let's go ahead to the next slide. Slide 4. This slide is about the blocks inside the repeat loop of a proportional line follower. The main idea here is that you have a target reflected light percentage, which is the midpoint between the black line and the white background. The robot constantly checks how far off it is from that target, so it knows whether to steer left or right. We multiply that error by a KP value, which is the steering sensitivity. Positive numbers will make it steer sharply to the right edge of the line, and negative numbers will flip it to follow the left edge. It smoothly adjusts its steering based on how far off the line it is. Let's move on to the next slide. Slide 5. This is an optional stack you can create to really fine-tune your line follower. It's taking 1,000 readings from both the left and right color sensors, while the left sensor is on the black line and the right sensor is on the white background, and averaging those readings out. This helps you figure out the baseline for what black and white look like in your current lighting conditions. In this example, they got an average of 20% for the black line and 100% for white. In different lighting conditions, maybe the black line reads at 10% or white reads at 95%. This is a calibration step to make sure your robot knows exactly what black and white look like in your environment. Let's move on to the next slide. Slide 6. Here we have a line follower My block that follows the line for a specific distance. Because humans think in centimeters, but the robot's motors track distance in degrees, we use operator blocks to convert your requested centimeters back into motor degrees. Instead of telling the robot to go X motor degrees, you're able to tell it to go X centimeters, which is much more intuitive. You also have to choose the correct port for the color sensor. If you don't, this block won't work. Always double-check that your color sensor is plugged into the port specified in your code. Finally, the target reflected value at the top of the My block must match the values you measured for white and black at the start of your session. If you measured black at 20% and white at 100%, you would want to pick a target somewhere between those values, like 60%. Let's transition to the next slide. Slide 7. Besides using the color sensor to follow the line, you can also use it to recognize predefined colors as a signal to stop. Every color the Lego Spike sensor can recognize is permanently associated with a specific number. Rather than trying to remember all those numbers off the top of your head, you can create a list of color names and import it right into your Variables tab as a lookup table. That way, if you need your robot to stop on green, you just refer to green in the list and the system automatically knows which numeric code it corresponds to. It saves a lot of time and memorization. Let's move along to the next slide. Slide 8. Now we move on to the line follower itself that stops on a color. Because we've set up that list of colors, we can link it directly to this slide. Essentially, the My block you see here is designed to make the robot follow a line until it detects a specific color. Because we have our named colors list, you just type green or red into the red input bubble and the robot will know exactly when to stop. You don't have to remember any numeric codes at all. Let's shift to the next slide. Slide 9. The easiest thing to do is to make a line follower that follows a line for a certain amount of time. All you need to do is reset the timer, which is another sensor inside the spike hub. We then put a simple greater than operator block, and when the timer surpasses the time you've chosen, the loop will exit and the robot will stop. The problem with time is that depending on how much the robot zigzags, how charged the battery is, or tiny differences in friction, it might not cover the exact same distance each time. It's a simple solution that works well for rough distance estimates, but if you need pinpoint accuracy, you should combine it with the color sensor or motor distance methods. Let's go to the next slide now. Slide 10. This slide shows how to test all the different line followers you've created. It's focused on running a simple program to compare how your line follower performs under different conditions, allowing you to test different speeds and different KP values side by side to see what works best. All right, on to the next slide. Slide 11. This line follower that uses the gyro sensor is more difficult because you've got to follow a line while keeping an eye on the yaw angle inside your robot. If a course is snaking, we can use specific yaw angles as waypoints. You're essentially breaking the entire line-following task into direction change segments. Each time the robot completes a certain angle change, you reset the gyro sensor and treat the next segment as a fresh start. This gives you more control and means you're not just relying on time or a single long line-following run. In the My block code, you can see that we are not simply following a line up to our chosen yaw angle and then stopping. We're stopping early by adding 15 degrees to our chosen yaw angle when following a path to the left. We then use the manual turn block mentioned at the start of the presentation to finish off the move. It's like using a computer to automatically get a space capsule close to a docking port and then take over manual control for the final few meters of precision. Furthermore, there's a tricky boundary where the spike's yaw angle flips from positive 179 degrees to negative 180 degrees. If you're just using a simple greater than or less than condition to stop the robot, you get bugs at that wraparound point. Stopping the line follower early and finishing with a manual turn, My block ensures you account for overshoot and avoid those wraparound bugs entirely. Let's transition to the final slide. Slide 12. Both the last slide and this slide have My blocks with almost the exact same info on them. You've essentially created two separate My blocks because the logic is different depending on which way you're turning. When turning right, the yaw angle values get bigger, and when turning left, the yaw values shrink. You need a slightly different mathematical approach to handle each situation cleanly. That's why you have a dedicated block with a greater than operator for right turns and a separate block with a less than operator for left turns. It's a smart way to keep things organized and avoid making one huge complicated block that tries to handle both directions at once.